All right, let's dive into a really cool and honestly super important idea from computer science. It's all about how we can guarantee our technology is actually safe. And the key to it all, something called computation tree logic.
So let's start with a big question. I mean, a really big one. How can you prove 100% that a self-driving car will never, ever crash? Or think about a power plant or the computer on an airplane. How can we be so sure it won't make a huge mistake? We're not just talking about checking some possibilities. We need to check every single one.
And that right there, that's what we can call the code catastrophe problem. It's this massive, and I mean massive, challenge of guaranteeing software safety. Because, as these systems get more and more complex, making sure they're safe and reliable, well, that job gets exponentially harder.
You see, just running tests, even if you run millions of them, it's just not going to cut it. There's no way you can test every single tiny combination of things that could happen out there in the real world. And it only takes one scenario you missed, just one, for disaster to strike. So what we really need is a way to mathematically prove that a system is safe across every single timeline you can imagine.
And this is where Computation Tree Logic, or CTL for short, finally enters the picture. Now, it's really important to get this. CTL isn't a programming language like Python or Java. It's what we call a specification language. Basically, it's a super precise way to write down the rules for how a system is supposed to behave. And the best part, we can then use computers to automatically check if the system actually follows those rules in every single possible future. Okay, to really wrap your head around what makes CTL so powerful, we kind of have to change how we think about time. So ask yourself this. Is the future just one straight road ahead, or is it more like a giant intersection with tons of different paths you could take?
And this is really the core idea here. Most of the time, we think about the future in what's called linear time. One thing happens, then the next, like a train on a single straight track. But complex computer systems, they don't work like that. They have choices. They react to things. They operate in branching time. At any given moment, the system could go down a bunch of different paths, kind of like a train pulling into a massive railway junction, with tracks splitting off in every direction. And that's the key. CTL is built for that complex junction, not the simple single track.
Yeah, exactly. This quote just nails it. CTL doesn't run from this complexity. It leans right into it. The whole philosophy is that the future isn't a straight line. It's a massive branching tree of possibilities. And CTL gives us the language to talk about and to analyze that entire tree. And this isn't some brand new cutting-edge thing. The idea actually goes all the way back to the early 80s. It was first introduced by Clark and Emerson in '81, and then, believe it or not, developed totally independently by Quealy and Sifakis just a year later. What they came up with back then laid the groundwork for what's become an absolutely essential tool for making sure the critical tech we use every single day is safe.
All right, so how does CTL actually do this? How does it reason about this whole tree of futures? Well, it boils down to two really powerful but surprisingly simple tools.
The secret sauce is something called path quantifiers. These are like the basic building blocks for any statement you make in CTL. And they let us ask two very different, but very important, kinds of questions about that whole railway junction of possibilities we were talking about.
Okay, first up is the A quantifier. The easiest way to remember this is A stands for all. When you use an A, you're making a huge claim. You're saying something is true for every single possible path going forward. No exceptions. It's like standing at that railway junction and asking, do all of these tracks, every last one, end up at a safe destination? This is how you prove something is absolutely always safe.
Then you've got the other side of the coin, the E quantifier. And yep, you guessed it, E is for exists. This asks a totally different question. It's not about all paths anymore. Now we're asking, is there at least one path, just one, that could lead to a particular outcome? This thing is basically your ultimate bug hunter. It lets you ask, does there exist even one single, maybe super unlikely path that ends in a system crash?
So, okay, we have this awesome language for asking really precise questions. But how do we actually get the answers? Well, that's where an automated process comes in. And you can think of it like a tireless digital inspector.
The process is called model checking, and it basically works in 3 steps. First, you have to model the system. The engineers create this perfect, formal map of every possible state and every connection. That's our railway map. Second, you define the property. You write the rule you want to check using a CTL formula, something like, along all paths, it's impossible to reach a crash state. And then the magic happens. A computer algorithm takes that map and that rule, and it just goes. It explores every single path and corner of that map to see if the rule holds true. It's a completely automated, exhaustive proof.
Now, I know what you're thinking. Checking every possible future, that must take like forever, right? But here's the really amazing part. Computer scientists figured out that this problem, for all its complexity, is actually what we call P-complete. And what that means, in simple terms, is that it's surprisingly efficient for a computer to solve. It's this efficiency that makes the whole thing practical for the massive systems we use in the real world.
And things got even better from there. A huge breakthrough came along called symbolic model checking. This basically let computers verify systems with an absolutely insane number of states. The trick was, instead of looking at every single state one by one, this technique let them group massive collections of similar states together and check them all in one go. This is what took CTL from being a cool idea in a university to a total powerhouse in the industry.
So, CTL is obviously a huge deal, a real cornerstone. But it's not the only tool in the toolbox. It's actually part of a whole family of verification logics, and each one is specially designed for a different kind of problem.
For instance, you've got CTL star, which is kind of like CTL's more powerful big brother. Then there's PCTL, which is awesome because it adds probability. So you can ask questions like, what are the odds of a failure happening? You've even got ATL for systems with multiple players, like a whole fleet of self-driving cars coordinating, and DCTL, which is built just for systems designed to handle faults. The point is, there's a specialized tool for pretty much any verification challenge you can think of.
So, here's the main thing to take away from all this. Computation tree logic and all its cousins, they're not just some obscure academic exercise. No way. They are fundamental, essential tools that real engineers use every day to build the amazingly complex and reliable tech that runs our world. We're talking everything from the chip in your phone to the software on a spaceship.
And that really leaves us with a huge question for the future, right? As our systems, and especially AI, get more and more complex, as they start learning and behaving in ways we can't always predict, that branching tree of possibilities just explodes in size. So you have to wonder, what new kinds of logic, what completely new ways of asking questions are we going to have to invent to make sure we can actually truly trust them?